This time we're going to be looking at continuity of functions between metric spaces. So you see I have two metric spaces here, x with a metric d, and another metric space y with a metric d prime, and a function f with domain x and codomain y. And what we're saying is that f is a continuous function. You may have seen continuity before in real analysis. This is a more general idea of continuity for not just real functions, for any kind of function between different kind of metric spaces. So we say that f is continuous at a point c if we take any positive radius epsilon, then there exists another positive radius delta, such that we can squeeze a ball. If we take a ball of radius delta around the point C, then we can squeeze that ball into a ball of radius epsilon around the point F of C. And we'll just dive straight in with an example, because this is a really crazy concept to grasp. So let's just pick a simple function. Let's pick a real valued function. So function f that goes from R to R, and I don't really care what it is. I'll just draw a random one. So it probably goes something like, say this, and then goes whoop, jumps to here. And so you can see kind of what I mean by continuous and discontinuous. You've probably seen this in real analysis before, but what does it mean actually in terms of our definition? What are we actually saying here? Well, okay, so this is a real axis, and this is a real axis. And so what's our definition here? Well, we want that f is continuous at a point C. So say this is the point C. Just pick a point C. We want that given any radius epsilon greater than 0, and remember this is going to become a ball, an arbitrary ball of radius epsilon around the point F of C. So this is a ball in the codomain. So on the vertical axis this will be. So an arbitrary ball of radius epsilon in the codomain around F of C. So here, say this can be as big or small as you like. So what we want is we want to find it. We say it's continuous if we can find a ball of radius delta around C in the domain, such that when we pass this ball through the function, then it will fit inside the ball in the codomain that we've picked. And we can find a ball that fits inside here. We just take, for example, this ball. This ball of radius delta, don't care what delta is, but this ball, when you pass it through the function, it'll only go as high as well, this is about here. It'll only go as high as here, and it'll only go as low as, what's the lowest point in this section? Well, here, I guess. It'll only go as low as here. So this will fit nicely inside our arbitrary ball that we've picked in the codomain. So how does this fail then? When do we say that a function is not continuous at a point? Well, let's take now this point. So say this is the end point. Okay, this is the end point, and that's at the end of the line. So there's nothing here. It just continues on underneath. So let's take a ball of radius epsilon, arbitrary ball of radius epsilon around the point F of C in the codomain. So this ball, say for example, and we're looking for a ball of some radius in the domain. So let's say some ball. We're looking for a ball which will, when we pass this set of points through the function, will fit inside the set we've chosen in the codomain. But notice that this set contains these points. So the lowest this goes, the lowest point that this function takes when we restrict it to this set is here. And the highest it goes is here, but this isn't important. So the lowest it goes in here is here. So it's not going to fit inside this yellow ball here. And no matter how small we make this orange ball, it's still going to contain points that are outside the scope of this yellow ball. You know, even if this orange ball was really super tiny around the point, it's still going to contain at least one point from down here. So it's never going to fit inside this yellow ball. And this really is what we mean when we say it's discontinuous at a point. So let's look at a different function. Let's take the inclusion mapping. So f goes from z, the integers, with a metric d to the reals with d prime, where d is the discrete metric and d primed is the Euclidean metric. Okay, so visually it's gonna look like this. We're gonna have the domain is z, so a series of points, and the codomain is real. So this is z and this is r. And so I said this was the inclusion mapping, so this will be that f simply maps x to x, where this is an integer but this is a real. So this is gonna go like something like this. Something like that. So is this continuous or discontinuous? Well, let's take a ball of radius epsilon around some point f of c. So we pick a point c. Let's say this is our point c, and f of c is obviously in the codomain. So we take a ball of radius whatever around f of c. So this is here. Now, in order for this to be continuous, we need to be able to find a ball of radius anything around c in the domain, such that when we pass it through the function, it will lie exactly within this yellow ball of any size. So let's just make this yellow ball actually a lot smaller. So like that, right? So this is our new yellow ball. So it's really tiny. Is there a ball of radius anything in the domain which, when we pass it through the function, will lie within this open ball in the codomain? Well, remember that in the discrete metric, which is the metric we have for our domain, every isolated point is an open ball. So this point is its own open ball. So of course when you pass it through the function, it's going to lie within this yellow ball in the codomain, because the image of this point is the point which we built the open ball around. So in the next video we'll do an alternate definition of continuity, which will help us prove some really powerful theorems.